Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you very much for coming. Today we will have an exciting talk by Professor Deborah Shah from MIT. Professor Shah is currently Associate Professor in EECS department at MIT. His research interest is statistic inference and network algorithms. He has received a number of awards, including the IEEE Infocom Best Paper Award in 2004, ACM Symmetric's Best Paper Award in 2006. He received 2005 George B. Danzig Best Dissertation Award from Informs. He's also the recipient of the first ACM Symmetric's Rising Star Award in 2008 for his work on network scheduling algorithms. Without further ado, let's hear what he has to say about inferring rankings under constraint sensing.
Okay. Thanks, Jen. Thank you for hosting, and Sujipta for very happy to be here. So what I'm going to talk about today is inferring popular rankings from partial or constrained information. The talk is going to be about learning, say, distributions over permutations or rankings. But as the talk will proceed through a few examples, I'll mention that the type of things that we are discovering here are likely to extend to a more general setup of learning some full information from available partial information using some additional structures. Okay, this is joint work with my student Shrikant Jagarbudala at MIT. Again, feel free to stop me during the talk because I might be using a notation that may not be clear, and question answers will be very helpful. Okay, so to set up the context, let me start with very basic motivation and very simple examples. So here's the first example. It's of election scenario. So think of pre-primary, which was not too far in the past or maybe not too far in future now. Let's say we have many candidates that are in the race, and we want to figure out what are the popular rankings of these candidates in voters. So think of n candidates, say Obama, Clinton, Richardson, and so on. These are the candidates who are likely to be in the race, and every voter has implicitly or so consciously or subconsciously some form of ranking of these candidates in mind. Okay. And we want to figure out what fraction of voters believe in certain ranking. Say, what fraction of voters like Obama as first, Richardson as second, and Clinton as third, and so on. Now, if you have n candidates, the total number of such rankings will be n factorial. So even for n equals to 4, this is large number, like 24, right? So in general, this is lots of candidates. If you have lots of candidates, then just too many possible rankings. And if you went and asked people saying that, could you please tell me, do you prefer this ranking or that ranking or that ranking? It's impossible. And it's impossible because I, as an individual, may not be able to sort of consciously put down those rankings, or I may not have incentive to tell you. Or worse yet, if you are standing outside Times Square and taking a poll, then the person who is coming out of the subway has just 3 seconds to answer your question. So in that situation, the likely answers that you might obtain from people, say through polls, would be of the following type. I'd say, do you like Obama over Hillary or not? Or who is your favorite candidate? Or more generalization of this would be, do you like Obama as a third candidate? And so on. So these are the type of partial information that will be available. And then based on this, you want to figure out what fraction of people believe in what rankings. Okay, let's take another example, which is where similar thing happens. So think of ranking teams in a sports leagues. For example, say football league. Okay, there are n teams. Not all n teams are going to play with each other. Some of them are going to play with each other, and over time we'll collect different results. And based on this, we want to come up with ranking. Now, first I want to argue that there may not be one global ranking, because a team may be very strong, but let's say one of the days its quarterback is ill, or let's say broke up, then maybe the team may not perform as good as its native strength. So there may be some form of a distribution over rankings that will be represented in the results of the various games. So what we want to do is that looking at the results of the games, that is what fraction of time team X defeated team Y, we want to figure out what is the distribution over rankings on the teams. Okay? Any questions? I'm just going through simple examples, and hopefully the examples are making sense. Okay. All right. So let's take another third example, and this is different from ranking, and this is where my comment was that some of the things we would like to do are likely to extend to more general setup rather than just ranking, but this talk will be only about rankings. So network measurement case. So let's think of, you have a network, and a network has, let's say, n flows active. So flows are sources and destination, and they're sending data between sources and destination. And the type of information or measurement that you are gathering are aggregate type information. So for a given link, you would know how much demand is passing through, but you may not know which flows are sending what demands. And this is primarily because if there are quite a few flows going through one link, you may not be able to measure them. It's just too much to do. So given this kind of aggregate bandwidth utilization information, what you would like to figure out is which are the flows that are active and how much is the demand that they're sending. Okay. So all these questions, in a nutshell, are of the following type, that there is some partial information that's available that's constrained. The constraint because in case of polling, you are getting answers of X, candidate X greater than candidate Y, or so on. In network measurement, only links allow you to give aggregate information. It's a constraint in that sense, but what we would like to do is we want to infer the complete information, as in distribution over all rankings based on, say, comparison data, and so on. Okay? Yes?
Something like also possible, like a stable marriage situation in which there's no stable marriage solution. It's like find the most least unstable marriage, something like this.
Maybe there is some connection, but yes.
What if there's like three, let's say like in your ranking thing?
Yes.
If there's like A, B, and C, then A, if you have A, B, then A beats B, then if you have B and C, B beats C, and
C beats
C beats A, something like that.
Correct. So like concerted paradox. So there sort of the question is that if that type of situation happens, the following is not possible. So the question is that what if the situation is A beats B, B beats C, and C beats A? Then if you have just that type of information, then there is no one ranking. There is distribution over rankings with support on one ranking is not possible. And that's exactly what I want to argue, that those type of situation arises because hypothesis is that there is only support is just one ranking. Here what I want to say is that when you sort of relax that requirement or get out of that mode of thinking and now look for a general answer where I'm looking for a distribution over space of rankings, then there will be a reasonable way to answer that question, and that will alleviate actually some of those classical paradoxes that are there in the sort of political science literature. It's a great question. Any other question? Okay, so bottom line is that in all of these questions, we want to learn something from partial information. And this type of things, of course, if I have a distribution which is uniform over n factorial permutations, and if I'm giving you only comparison information, there is not much that I can do about it. I just have little information. So the right question to ask is, given this type of partial information, when is the recovery possible? And if recovery is possible, how can we recover it? Okay. All right, so now let's just put a little bit of formalism around it. So let's start with very simple examples. Okay, so I'm thinking of, say, the case of election and two candidates. Now, two candidates can be ranked in two ways. Candidate 1 ranks to candidate position 1. Candidate 2 gets ranked to position 2. So this is my notation of bipartite graph, and this is how I'm going to use it throughout the talk. So this is one ranking. The other ranking is candidate 1 is ranked in position 2, and candidate 2 is ranked in position 1. Okay, it's a very simple thing. Now let's say P1 fraction of people believe in this ranking, and 1 minus P1, say that is P2 fraction of people believe in this ranking. Okay, so then in case of comparison information, the type of information we will get thanks to polling would be of the following type. What fraction of people rank 1 over 2? In this simple setup, it would be probability, assuming that we are choosing people at random, so probability that 1 is ranked better than 2, which is P1 in this case. Okay? And similarly here, the fraction of people who believe 2 is greater than 1, which is P2, or if I write in a matrix form, this is the information that I have available. This is the native information, that is P1 believes in this first permutation or ranking. This is second ranking. And this column corresponds to the first one, and this column corresponds to the second one. Okay. All right. So this is just a setup. And more generally, if you have n candidates, you have n times n minus 1 possible pairs. Of course, half of them are redundant because we are thinking of distribution. Because if I know pi greater than j, then 1 minus pi greater than j is pj greater than I, right? Okay. So this is the type of information we have available, and the total amount of possible rankings, or the distribution over which this is, that space has n factorial thing. So this is usually very, very long, and this is very, very short. Okay, so the matrix that you're going to see is very thin. Okay, let's see another example. So here is a little more detail, and this is the example that I'm going to use throughout the talk, or this type of example to explain the results. So again, going back to the same situation, this is ranking 1, this is ranking 2, P1 fraction people believe here, P2 fraction people believe this one. I'm going to generate this bipartite graph where every edge has a weight. So for example, this is fraction of people who believe that candidate 1 should be ranked in position 1. And that is, in this case, is just this edge, because it's only this ranking that contains it. So y11 is nothing but P1, and so on. Okay, and in this situation, we have this. This is the information yij, which is given by this matrix times the original data. And this, again, as before, this matrix is, the columns are nothing but correspond to each different permutation. Questions? Okay, so here again you have n square amount of information available, and total possible positions in this distribution or support is n factorial. So we have this information available, we are trying to recover this. It's a humongous task. Okay, one more example quickly. This is this network measurement situation where, let's say I have 2 links, and let's say possible sources and destinations are any of these situations, like n nodes, and any other n minus 1 nodes can be its destination. So these many possible flows. Each link provides you aggregate flow that's passing through that thing. So for example, here, through this link, only flow 1 is passing with amount P1. Through this link, it's P1 plus P2, that's amount passing. So that's the observation that you're going to make as y12 and y23. And again, this is related to the flow matrix times the graph adjacency matrix as follows. Okay. Any questions? So again, we have a situation where this is tall, this is thin, and this is tiny. And we want to recover this out of this. Okay. So in a nutshell, we have y equals to ax, where x is, let's say, capital N dimensional. In case of ranking, it was n factorial. And the observations are m dimensional. In the 2 examples I gave you, they were n squared dimensional. It's A is a 0, 1 matrix, and AMI says that 1 if that mth component is represented by ith permutation, in a nutshell. Okay. The question is, recover x based on observation y and the knowledge of A. It's like inverting. So if we had this big and this small, possibly it was likely, but it's the inverted problem. So clearly we need more constrained question, as in general this is hard to answer. So here's a classical approach. It's a philosophy, right? Occam's razor. That is, you have observations y, you can find various explanations, that is x's, that are consistent with your observation. The one that you want to find is that is simplest. One way to think of simplest is sparsest. That is, find x that has smallest support. That is, find an x with number of positions with xi not equal to 0, which I'll call L0 norm, is smallest. And why this type of approach have a likelihood in many of the examples that I discussed? Well, for example, if you think of election situation, you as a voter do care about few issues, and those few issues decide your rankings. So irrespective of number of candidates, there are few rankings which are likely to be dominating. Similarly, in sports league, you have teams have native strengths, and most of the teams are going to be ranked according to their native strengths, but because of some uncertainties like quarterback's illness, there will be the rankings that you will observe, at least in the results, will be some perturbation of these native rankings. So it will be again likely to be sparse. Or again, in network, in situations, it's likely that there are few flows which will be active, though there are many possible flows can be there. Okay, so given this, our now problem is left is that we want to find out a sparsest solution consistent with our observations, and the question is that when is that sparsest solution representing the real situation? Now this is to put in formalism, find out a z that is consistent with your observation in this sense, that has minimum support. Okay, this is the L0 optimization. Okay, now this is a very classical approach, and there are many situations where people have used it. I'll sort of allude to two of them. One is the communication setup, or in case for decoding. So think of, you have a code word or a message that you're going to transmit over a noisy channel, and at the end of that you will receive a noisy signal. So there are, let's say you transmitted n bits, out of them few of the bits are flipped. So there's a sequence of 0, 1, some of them are flipped now that you received. Now you want to figure out which ones are flipped. Okay. Now in case of linear coding, essentially it corresponds to finding out the vector of, so think of a vector of zeros and ones, where ones represent the positions where bit flips have happened, zeros otherwise. It's called syndrome. What you want to do is you want to find out a syndrome that is consistent with your observation that you have received. Okay, and this type of L0 decoding would correspond to looking at a code word and looking at the received signal and find out the closest code word to it in, say, Hamming distance sense. Okay, so that's let's say quick relation to why this type of problems have been well studied in coding. More recently, this has become central in the topic which is popularly known as compressed sensing, which many of you will know. Is that here the question is, again, you have observations, you want to figure out X which has sparse support. Okay, and in all of these situations, the primary quest is of the following type. You want to design matrix A. In context of coding, you want to design code so that you will be able to recover X, that is the original thing, based on observations, as long as X is sparse. That is, the original X had few positions where it was non-zero. Okay, and in many of these cases, the way you design A, sort of solving actual L0 optimization becomes easy, because in general this optimization is a hard problem. Okay, so this has been generic philosophy. But now let's ask our setup. We have the same situation, y equals to ax, but A is not design. You can't design A. A is given to you, and so this type of things are unlikely to work. Let me just quickly give a small summary of what type of approaches that's popular here. So, and it can be useful for our purposes, because we are not going to design A, but if the way you prove that A's are good is you sort of show that A has good property, and the good property is called, roughly speaking, a restricted isoperimetry property. Or equivalently, what it says is that if you have a matrix A, and if you look at any k subset of columns out of these A, then they are essentially orthonormal. So they are linearly independent and they preserve norm. It's like identity. And if such is the case, then you can recover X using this optimization very quickly. Okay? But in our case, A we cannot design, but maybe we can ask the question, does A have this property? Because if A has this property, then at least our quest is over. Okay. Did I lose half of you? Yes?
I thought with compressed sensing you do random projections, right?
Good.
So do random matrices naturally have some properties similar to K-ref or?
Correct. So one of the approaches to prove that, okay, so in compressed sensing or say linear coding, you do random linear coding or random projections, you come up with a matrix A, then you prove that actually this matrix is going to be good because it has this property. So while we can't design matrix A, but maybe our matrix by design has some such property, and hence it may lead to good answers. Well, as it happens, the choices of A that we have don't have this RIP property. Now instead of proving that, I'll just give you a simple counterexample that will explain it. Okay. So let's think of this simple counterexample. It's 4 candidates. I'm thinking of marginal information. That is, I have 4 candidates on left. These are positions. This edge represents candidate 1 ranked to position 1. And this number 0.5 says that 0.5 fraction of people believe that candidate 1 should be ranked in position 1. And this is the whole information that I have. So this is my Y. Now here is a simple counterexample which says that, well, there is 2 ways to produce this Y, in which the support is 2, which is the minimal possible, and it has this equal probability. So this ranking says that candidate 1 is ranked 1, candidate 2 is ranked 2, and so on. Here it says 1 is ranked position 2, 2 is ranked position 1, and so on. Versus the flip one where I took this on this side and this on this side. So now I've got 2 possible decompositions of this thing with minimum support. And so L0 doesn't have a unique solution, and hence sort of it's not going to be able to recover what you want. Okay, so it says that it doesn't even have 2 RIP property. So in some sense, the best recovery that we can do would be k equals to 1, which is rather tautology or trivial. Okay, so this is one situation. Just to drive the point home, here is another situation where it's a network measurement case, where there is a 3-linked network, and you're going to measure load 2 on this link, load 1 on this, and load 1 on this. This can be done 2 ways. If you have one flow going like this across, and there's one flow here, which will give you the same loading. Or this is another example where it will happen. So again, so is that the type of situation that we are going to see, it's impossible to expect some good RIP style property. So now the question is that, well, we have this kind of situation, RIP property is not going to work. That means adversarially we won't be able to recover anything interesting. So what can we do? Now what I'm going to do is I'm going to give you a sufficient condition under which it's possible to recover X using L0 optimization as its unique solution. And I will give you under that condition a very simple algorithm to recover that X. It's one thing. Well, that condition can be totally bizarre and useless. What I'll try to argue in the second part is that, well, indeed that condition is not bizarre. Actually, if you take a random model, a natural random model, then these conditions will be satisfied, and these conditions will be satisfied in an optimal sense, and I will explain that optimality later. But what this will suggest is that while the way RIP approach goes, adversarially recovery may not be possible, but for most sparse situations recovery will be possible. So it says that counter examples that I just produced to you, they're actually very special. And if you lay down a uniform distribution over space of sparse supports, then actually you will not see those counterexamples with high probability. Okay, and this is like in coding. There is this, if you know, there is this dichotomy between adversarial coding versus probabilistic coding, where for adversarial decoding, for graph codes, you need expansion as necessity, but for random error, you don't need expansions as necessity. That's roughly related to this because, okay. All right, and then finally I'll discuss some more things where here we will talk about specific type of informations like comparison, favorite candidates. But then what is the dichotomy of this type of information? Is there a natural way to ask all sorts of information? And depending on amount of information you give, my recoverability should increase. So what's the right trade-off between information and the recoverability? I'll discuss those connections here.
Question?
Yes?
So can you go back to the previous or one of those examples? So here, right, I mean, the answer would be you would give a 0.25 probability to each of these rankings, right, and 0 probability to the other rankings, right? Is that the correct answer?
Yes. So 0.25 to this, 0.25 to this, and rest of the 24 minus 2, 0.
No, actually 0.25 to each of the 4 things, right?
So then, okay, so one another answer would be with support 4.
Oh, yeah.
Okay, so answer 1 with support 2 would be 0.5 probability to this, 0.5 probability to this, and 0 probabilities to rest of the 4 factorial minus 2, that is 22. Okay. Answer 2 would be the similar with support 2. Answer 3 could be support 4, where 0.25, 0.25, 0.25, 0.25, or choose any other reasonable combinations.
Yeah. And why is that? So you're trying to find an answer with support 2? Is that?
I'm trying to find an answer with the sparsest support.
Okay.
Because that will be the L0 minimization.
Okay. Got it. Okay.
And if I had L0 unique solution to L0 minimization, and since Y is generated by the thing that I am looking for, then I have proved that L0 minimization recovers what I'm looking for. It's good. This is good. Is that helpful? Okay. Okay, so now let's move on. So I'm going to tell you sufficient conditions. At first, they may look a little bizarre, but hold on, there's a promise that I'll explain that actually it is satisfied by a natural model. Okay. So let me walk you through sufficient conditions. Sufficient conditions has 2 parts. Okay, this is a sufficient condition for proving that the L0 optimization problem that I stated has unique solution, which happens to be the original X that I want, and there is an algorithm that will recover it very easily. Okay. First condition says unique signature. So let me just use an example to say what unique signature is, and then we'll go back and read it again. Okay, so okay, let's do the following. So let's say going back to the marginal thing. So 3 candidates. This is n square. There is 9 pieces of information. This is candidate 1 ranked in position 1.9 fraction of people, and let's say original underlying data is this. That is, out of 3 factorial, which is 6 possible permutations, these 3 permutations are likely, or these 3 rankings are popular among people. 0.1 fraction of people believe in this, 0.2 fraction of people believe in this, and 0.7 fraction of people believe in this. Rest of the rankings are not popular. Now, the unique signature says the following, that in the support of this X, there is these three rankings have unique edges, and those unique edges are these pink edges. So what do I mean by unique edges? That is, this edge is present, or this type of ranking is done only in this one and not in other one. What that means is that candidate 1 is ranked in position 2 only by this one and not by these other 2 non-zero mass ones. Of course, there will be other permutations or other rankings which will rank 1 to 2, but they have 0 mass, so they are essentially not visible. Similarly, the second one says that candidate 2 is ranked in position 2. This doesn't rank, and this doesn't rank that way. And this is the third one. Okay, and that's what it means. Okay, so this is unique signature, or in a more general setup, irrespective of rankings in y equals to ax form. Sorry, I think I should do this way. Y equals to ax form says that for every I that is in the support of x, there exists a row in which only AMI equals to 1 for this I, but for all other j with non-zero support, they have AMJ equals to 0. So in a nutshell, what it will mean is that when I will apply A to this x, ym will be equals to xi. So on one hand, it says, well, I just told you xi, right? But on the other hand, I haven't told you really which xi it is, because you don't know which ym it is, because you don't know which other j's are. So all it says is there is a promise to recover information, but it's not obvious how to do it. Okay. The other one says linear independence, and linear independence, it's essentially what we think of as linear independence, but with the restricted sense. That is, you look at all these xi values, take any combination of these with ci's coming from natural numbers, positive and negative numbers, but with values between minus x0 and plus x0. Okay. As a special case, what it will mean is that, and implication of this would be that look at all xi that are not equal to 0, and let's say since they are first I'm ordering them as first 2, 3 up to x naught, and I'm taking any partial sum or subset of them. All of these partial subset sums are distinct. Okay. So let's say going back to this one, what are the possible partial subset sums? It's just this element or this element or this element. So these are 0.1, 0.2 and 0.7. Another subset is these two guys. So 0.1 plus 0.2 is 0.3. Another subset is 0.7 plus 0.2 is 0.9. And third subset is 0.7 plus 0.1, which is 0.8, and 1. And all of these are distinct numbers, right? Okay, so this is the situation. And when you have these conditions satisfied, then we will have an algorithm, and this also these conditions will be satisfied under the random model that I'll describe. Okay, so now I want to tell you the algorithm. Okay, so let's go back to this example. So here's what I will do. First, I will look at the data I have. So remember, we have this data. We don't know how many underlying permutations that are there that have generated this. We don't know their values, and we don't know which ones are there, right? But we want to figure out all those three. That is, there are 3 permutations that are generating this. Those 3 permutations are these precisely, and their probabilities are 0.1, 0.2, and 0.7. To do that, I'll take this data and I will sort them. So that is, 0.1 is the smallest number. I'll take the smallest number first. Look at the edges with smallest number. Now, based on the property, that unique signature and distinct linear independence, or say subset sum property, I want to argue that the 0.1 must be the probability of this permutation with the smallest probability. Because, okay, let's think. Since we know that y equals to ax types and a is 0 or 1, each y, that is value on each edge, is possibly sum of few probabilities. There's pi1, pi2, pi3, pik. Okay. Since there is unique signature, what it means is that there exists an edge which has exactly the value which is equal to p1, which is the smallest. Okay. So that means that if I sorted this whole thing, then the smallest numbers will be the ones which are equal to p1, and those are the edges which belong to the permutation with smallest number. So far so good. So we just got started, right? Is this clear? I really hope that I will be able to convey this algorithm, because if I don't, then I think that there will be a failure of the talk. So please feel free to ask me questions.
And since it's unique, right, then you can remove it.
Correct.
Yes.
Good. So now what you will do, as you said, is that sort of now then we know that these two guys here, these two guys are 0.1 probability edges. They must belong to first permutation. And so here is what we do. We generate first permutation with, of course, here it's redundant, but let's say the edges that we have learned, and we put them and we assign its probability. So we have just got started. Now let's sort of try to repeat this type of algorithm. We remove those 2 edges from this. Now look at the rest of the edges with the rest of the weights. Look at the second smallest now. Second smallest here is 0.2. Okay. So 0.2, have 2 possibilities, right? Again, it can be from P1, of course it's not P1, or it can be from P1 plus P2 or P2, right? Of course P1 plus P2 will be bigger than P2. So this must be coming from P2. Okay, so by the same argument, we create another permutation with probability 0.2. Let's sort it again. The third is 0.3. Okay, 0.3 is P1 plus P2, and we know that unique subset sum property. That is, if it's P1 plus P2, it can't be equal to Pi1, Pi2, Pik. Okay, so that means it has to be from P1 plus P2. That means we'll put these 2 edges into these 2 permutations. So in some sense, we are done with this one. We're almost done with this one. Now we look at the rest of the edges. Now we come with this edge. Now what are the options? Well, options are P1 plus P2 we already learned. So either it's P3, okay, in this case it's trivial, but in general what can happen is the following. At any point of time when you are at the algorithm, you have discovered P1, P2 up to Pk. Now the number that you're looking at, it can be either one of the subset sums of these first k elements or Pk plus 1. Those are the only options. So either you discover edges of some of the combinations of permutation that you've already seen, or you're discovering a new permutation. So that's it. So in this case, 0.7 cannot be P1 plus P2, so it has to be P3. So you discover them, and then the last one, you know it's P2 plus P3, and that's it. It's the end of the algorithm. Any questions?
So what is the complexity? You have to keep these running subset sums and stuff like that, right?
Mm-hmm.
Is there some efficient way to be thinking about this so you can do this in polynomial time?
So subset sum by itself is a very hard problem, but for this you need to do it approximately, and for approximate there are sort of fully polynomial time approximation algorithms. Good question.
What's the dimensions of the table?
Sorry?
Perhaps the dimension in the table. N variables.
Exactly. That's right. Yeah. Thank you. Okay, so that was the algorithm. Now, if you see, there is not much as far as structure of permutations that I have used here. It's just the fact that as long as you have these two properties, this unique signature property and subset sum property or linear independence property, this algorithm is going to work. Okay. And the theorem is that as long as those two conditions are there, L0 optimization is unique solution. That unique solution is equal to your original solution, and this algorithm will recover it. Okay, so now the question is that how good or how bad this condition is. Okay, so let's, we know that this type of conditions are not going to be true adversarially. I just produced a counterexample. So let's look at the next version, that is randomly. So here is a random model. So the random model goes like this. So let's say I want to generate a model with sparsity k, that is k non-zero elements. So in case of permutations, here is what I will do. I have n factorial possible permutations. I'm going to choose k permutations uniformly at random out of them. And for each one of them, I want to assign probabilities, p1, p2, pk. And p1, p2, pk, here is how I'll generate. First, I'll generate numbers uniformly at random, say from an interval a to b. Then I'll sort of normalize those numbers, that is, sum them up, divide by the summation to each number, and then I will obtain probabilities. And that will be my model. The question is that when are these sufficient conditions satisfied? Or more precisely, for what values of, up to what values of k, these sufficient conditions are satisfied with high probability, so that we can recover the original x using the algorithm. Okay. Now, of course, we know that adversarially it's not going to be satisfied for even k equals to 3. But for random model, here is what's going to happen. So I told you the marginal information setup, where candidate I ranked in position j. And this is true for all ij's. In that situation, up to sparsity n log n, you will be able to recover, the sufficient conditions are satisfied with high probability, and hence the algorithm will be able to recover them with high probability. Okay. For comparison data, this works up to log n. Now, it's a little bit depressing in some sense, because you have the amount of information in both the cases you have is of order n square, and here you are able to recover n log n, here you are recovering up to log n. Now, this is sort of a small note about comparison. See, if you have k equals to 1, comparison is giving you all pairwise comparisons. So in some sense, it's equivalent to classical sorting problem. Okay, what here you are saying is that up to log n permutations you can sort simultaneously using this permutation information. And in a second, I'll tell you why I believe these are the right answers. Okay, and here is a bit of interesting fact that in addition to comparison, suppose I also give you the following fact that, so I as a polling person, I'm asking people information about compare people. Also, I'll ask some people, tell me your favorite candidate. Okay, so just with that bit of information, you will suddenly now go from n log n to square root of log n, square root of n. Okay. All right, so okay, so now there are two questions, right? One is the information that I just gave you, are they really tight, or sort of are they just artifact of my sufficient conditions? That's one. And second is, what is the generic way of asking these information, and what are the trade-offs depending on what questions you ask? So first, I want to let me answer you the first question. That is, what I'm trying to show here is that actually the results that we have here are not just artifacts of our sufficient condition, but actually they are necessary. Specifically, under random model, if your sparsity is scaling faster than n log n, then no algorithm, whether it's polynomial or exponential, doesn't matter, no algorithm will be able to recover the x with high probability. So it need not be L0, it need not be anything. No algorithm will be able to do it. Okay. All right. So that's the first part. Sorry, this is a typo. Oh no, sorry. This is not a typo. I was reading this one. Okay. So what this says is that for marginal information, n log n is this recoverability threshold in this random sense. Is before that you can recover it, after that you can't recover. And recovery is possible with the algorithm I told you. For comparison, I believe that it's log n is the sparsity, and if you're interested, I can talk to you offline why I believe that this conjecture should be true. Okay. Now, the question is, what about the various types of information, and what is the trade-off between the information and the recoverability threshold? So, let's just sort of think, what are other types of questions you can ask? In the case of elections, you can ask, say, well, I asked you first that candidate I ranked in position J, answer yes or no. But maybe now I can ask you more, it's like first order information. Now I can ask you second order information. Candidate I and I prime ranked in position J and J prime. Now tell me what fraction of people believe in that kind of thing. Okay, now it's more information, second order marginal. Or maybe kth order marginal would be I1, I2, IK ranked in position J1, J2, JK. Okay. Now, in these cases, question is that how would the recoverability threshold change? Yes, please.
So the recoverability threshold you said the previous slide, you said it's independent of your recovery condition, like whether it's L0 norm or some.
So recoverability threshold has two parts, right? One is when can you recover, and when can you not recover. So when can you recover? That answer, that is up to k equals to n log n, the sufficient conditions will be satisfied, and hence our algorithm will recover it. When can you not recover it, that's independent of algorithm, as in it's like in information theory sense it would be converse.
Yeah, for example, like the counter examples you gave, like
yes,
if you used L2 norm instead of L0 norm,
yes,
like the 4 thing would be the right answer. Right, giving each of them probability 0.25?
No, it may not be right answer if I started with the I generated that information using this x, which is sort of puts 0.5 support on those two cases.
Oh, okay. Got it. Okay, so basically there are two unique. Okay. Yeah.
Good. Okay, so see in this situation, since it's an underdetermined system of equations, there will be lots of solutions. The question is your solution that generated it is the sparsest unique? And in some sense, recovery part will say that yes, indeed, that is the case. Not recovery part will say, well, you can't do anything. So, okay. All right. So here is the situation. Now, question is that how will threshold change here? So here the threshold changes n squared log n. Here threshold changes n to power k log n. So there is some pattern. But again, the question is that are these the all type of questions that you can ask? Can't I ask some more complex questions? Okay, so here is a class of questions that I'm going to say that sort of have natural association, and these are essentially all classes of questions in some sense. Okay, now this type of questions come from the looking at the representation theory of permutations, but let me explain what these type of questions are and what type of recoverability threshold that comes up. So let's take number n. So n is the number of candidates. Now you can take different partitions of number n. So by partition I mean lambda 1, lambda 2, lambda r. Let's say they are decreasing, and they sum up to n. Okay, so for example, one partition would be n minus 1 comma 1. Is lambda 1 and lambda 2, they sum up to 1, so sum up to n. Or more generally, it's this type of partition and so on. There are different type of partitions you have. Now this partition, my claim is that it is associated to partial information of the first order information. That is, candidate I ranks to position j. This partial order is related to the kth order marginal information, i.e. this type of information. More generally, there are different ways to associate them. I'm not going to go into detail, but if you're interested, I'll be happy to talk to you at the end. In general, for every lambda, there is a class of information that's associated. It's like you take a function and you write down its Fourier transform, then different lambda represents different bases of that functional space. That's roughly the idea. Okay. Now, okay, so I just classified the types of partial information that you can get. Is lambda associates to a type of partial information. Now, the question is that how does recoverability threshold depend on this lambda? Okay. So for that, let me define one more thing. So given lambda, there is given type of partition of n. The number of ways you can partition n into this type of partition is this. Is n factorial divided by lambda 1 factorial, lambda 2, lambda r factorial. This is, if you remember from classical combinatorics class, right? So, okay. So for example, if you have lambda equals to n minus k 1, 1, 1, if you fit this formula, it's n factorial over n minus k factorial, which is essentially like n to power k. So now you see the pattern, right? I told you n to power k, for k marginal information, the threshold was n to power k log n. So now if you have d lambda, what should be the threshold? Think of k constant. What would be your threshold? Okay, it's d lambda log d lambda. Okay, so for large class of lambdas of partial information, this will be your recoverability threshold. So if you have a lambda that allows you to sort of look for different types of partitions, a lot more of them, you have a lot more information and you can recover a lot more. Otherwise you can recover less. Okay.
So what would be the lambdas for comparison?
Good. So comparison won't fall into this canonically, so but they will be implied, and hence it's conjecture of log n. And because this is okay, so this is a theorem that's d lambda log d lambda. But for comparison, what you can do is that you can take lambda equals to n minus 2 comma 1 comma 1, that is k equals to 2k's here, and then you can aggregate that information to obtain the comparison. Okay. But it won't fit naturally into this classification. In some sense, it's not sort of one of those canonical basis function. Okay, so that's essentially brings me to the end of the talk. So what I did today is I tried to do the following. I tried to understand when does the sparsest solution based approach will work for a question of inferring rankings, where rankings are to be inferred based on a partial information that's not engineered, as in measurement matrix is not engineered, you are given. The question is that when can you recover it? And what we try to do is that we try to study this approach under a natural model. The natural model provides this, for a large class of setup, it provides this optimal recovery threshold. So there are simple sufficient condition which tells you how you can recover them, and beyond that there's no way you can sort of recover the support or exact support. Going forward, what I would like to do is actually the examples that I pointed out, that is the network measurement case. Clearly there again network topology should play a role in when are the sufficient conditions satisfied and when they are not. And this type of simple sufficient condition, are they really the optimal, or are they really determining the recovery threshold? That would be interesting to know, and I don't know the answers. Okay. That's the end of my talk. Thank you. Questions? Yes?
Thank you. I think your condition is different from the RIP condition. The RIP condition is basically for arbitrary k
Correct.
columns. You have that space. Your condition is essentially, say, for the particular subset. As I have this.
Yes.
If you look at the particular subset, is exactly orthonormalized because it's 1 at some position,
Correct,
0.
correct.
And then on top of that, the thing works is your A matrix actually is one. All coefficients actually are ones.
Zeros or
Or
ones.
with 0 and 1.
Yes.
Is that the two essential properties of the work?
So, okay,
I
so.
really have a third condition, the linear independent. I'm not sure where that.
Okay, so. So let's say there is one condition which is the unique signature condition. As a part of that, there are two pieces. One is, as you said, the unique signature part or witness part, and the second one is A being 0 and 1. Question is that A being 0 and 1 necessary? That's one.
Yeah.
And the second one is where does the subset sum property or linear independence come up? Okay, so see, linear independence comes up because it allows you to sort of undeniably argue that if you're going from smallest to biggest, you're doing the right things.
Yeah.
So that's where it comes up. Okay. Now, as far as the A being 0 and 1 is concerned, I don't think it will really matter because one can sort of modify the similar things. And so, for example, A is not 0 and 1, but let's say it's 0, 1, or 2. Then you would argue things. Okay, there should be. Okay, you can add some clauses and make it work, but as it is, it may not work.
Okay, but
Yeah.
It may not work for the. It work for. I would imagine it would generalize to work for like 0, 1, 2 this year, but may not be generalized hard to generalize to continuous
Correct.
pairs.
Yeah, I think so. It may not. You're right. Yes.
So in the natural model that you have a probability distribution over rankings, right?
Correct.
How does that translate into individual guys? So does that translate into some sort of fairy tale saying probability, the first one is probability, or like the probability that candidate 1 is the highest rank is X, and probably the candidate 2 is highest rank is Y? Is there some, they translate into individual probability for individual people?
So because here the model is uniform, for most of the questions that you ask, that is, let's say, what is candidate 1 ranked in position 1, candidate ranked in position 2, they'll be uniform under this one. But you can think of other models like, say, perturbed model. Like I say that my random model is like this. Say, here is an identity, is a permutation, and then I'm going to do perturbation around it. So then you can define, so let me call it deperturbation model, saying that everybody is naturally I maps to I, but it can map to uniformly between plus or minus D of I. Now, under this random model, again, you can define appropriate threshold. So, for example, for marginal one, the recoverability threshold will be D log D. That's D is the perturbation, and actually that will be tight. So, for that model also, things will work out. As in, so in some sense, we have been in a hunt of situation where when does this type of simple sufficient conditions are not going to work, because it's sort of counterintuitive that this type of things are working. So there must be certain symmetry that we are using here that is sort of giving the exact answers, but we haven't been able to find it. So.
Any other questions? Thanks, the speaker, for the
Okay.
talk.
Okay. Thank you.